exercise 25 helicopter looping of the inertial course. Here we have an helicopter and with a state space model here with those equations and the equations of the control mechanism. And now we want to provide a simulation, a controller and a simulation that get our helicopter to the desired orientation RD and the desired total thrust. We also want to make a special maneuver, which is we want to make a looping. So I'll start showing the code here, and this is our code that controls that simulates the helicopter. And here we have a function control that takes some inputs here that we can define, which are theta type c, the Euler angles associated with its orientation, the desired orientation, and the altitude control. The altitude control is related to our total thrust. So I'll start the simulation by setting our z, our altitude, the desired altitude, to -30, and quite slow, quite little tilt in the theta direction, in the theta angle, which is of -0.2 radians. So he will try to go forwards a little bit. I'm going to run the simulation right now. And let me control here the frame. Okay, you can see that he's going upwards and moving forward a little bit. And by the time he gets to around the 30 meters of altitude, he maintains his position and only goes forwards. This means that our control here is working. And now I'm going to comment this and show another control, the control of the loop maneuver. Let me cancel this. And okay, we are going to perform our maneuver by setting 3 different missions. The first mission is going upwards, the second mission is looping, and the third mission is going downwards. So to go upwards, the helicopter only needs a certain level of thrust to gain altitude, and there's nothing pretty smart here. The magic happens in the loop part of the code, which is we are attaching time constraints to define the desired orientation of the helicopter. So this works on the assumption that our dynamical system is capable of responding fast enough to pursue this time constraint. So I'm going to run the simulation right now, and we are going to see the helicopter's maneuver. It starts gaining altitude, then he comes to 30 meters, and then he starts looping here. He goes completely upside down now, and then he finishes the loop and comes back to 30 meters of altitude. So this is our loop, but the thing here is that we attach it to a time constraint. So what if our mechanical system actually is not, what if actually we have a lot of inertia in our system and we cannot respond fast enough? We harden our time constraints in order to make things more difficult for the robot. So we are saying that he should be fast enough to respond 10 times faster than he would before. So this is, let's see what happens if we simulate with this. Oh, let me do something before. Let me come here and run Python 5. Okay. Okay, he start. Oh, it was pretty fast, but I'll run it again so we can see it better. He starts looping, and then when he's almost done, he stops and he goes all the way around, all the way back. Where's the simulation? Let me pause your. So let me run the simulation here. Let's see what happens when he gets to 30 meters. He start looping, and then when he's almost done, he goes all the way back, and he not actually performs the loop. That happens because our constraint was too much demanding for him. So showing that this type of constraint here to perform the loop is good, but not very good in a real case scenario. In fact, we would want to use quaternions so we avoid the gimbal lock problem when getting to 90 degrees of theta, which I can show right now what happens if we attach our constraint to the angle theta. Let's see here. We are going to see the gimbal lock problem. He will start turning, and then he stalls when he gets at theta with 90 degrees. And he cannot get out of this position. He's locked here. So the best approach would be to use quaternions.